Okay, the purpose of this video or two, is we want to derive a partial differential equation that describes the steady state temperature distribution of a plate. This plate, we'll draw something up here in a moment. This is a thin plate, insulated on top. Now what we do, we can also do for three-dimensional shapes. But we're just going to do it for the moment with a plate which is three-dimensional, but we treat it as two-dimensional, kind of a lamina. So okay, let's get something written down. So consider a thin heated plate. The heat is going to come from the edges. We're going to draw this rectangle in a moment. The heat is going to come from the edges, and there's going to be no heat loss from the top or the bottom of the plate. It'll be insulated in that regard, uninsulated along the edges. So it says there, consider a thin heated plate. The heat will come from the edges, insulated except at the edges. Okay. Right, so let's draw this plate. So we're going to have, to describe a point in the plate, well, I suppose the plate is actually three-dimensional, but we're going to make the assumption that it's very, very thin. And what that means is, if the plate is thin, there isn't much temperature difference. Say this is the top and this is the bottom, and you got the middle. If the plate is thin, there's not much space for much temperature difference between those places. So let us just draw the little, it's very thin. Even this is more exaggerated than it should be. So hopefully here you can see what I mean. So as I said, this is even exaggerated. It's a 3D object, very, very thin. Okay, so the weight of it we're calling delta Z, I think. And as I said, because it's very thin, if you're describing a place in the plate, you just have to specify an X and Y coordinate. You don't have to talk about how deep into the plate, because there's not much, there's not much difference between, say, the top and the bottom and the middle. So you just talk about, okay, the temperature at this point. So we need an X and Y axis. X and Y. And what we're going to do is we're going to chop this thing up. And this idea of chopping something up into loads of little pieces, I probably call it meshing here. It's also called finite element kind of thing. Whatever. Now, we're going to assume that we can chop it up into square pieces, a square grid, and I am probably not going to draw all the things, but I want you to imagine that I've chopped it up into loads and loads of different little squares. And the squares, as I said, actually I don't even think they have to be squares, but anyway, we'll do that. So imagine chopping up into loads of pieces. Now I won't do all of them. I won't do many of them at all, in fact. So like chop, 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 chop. Chop, 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 chop. And keep on going. And chop in the other direction. Chop, 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 chop. And chop, 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 chop. Anyway, let's just take a typical element. They should be parallel to the bottom. Take an element in the middle, because it's not clear what I'm doing yet. So this bit here, this is actually a little rectangle. Well, actually not a three-dimensional rectangle, because it does have a thickness. So imagine, what can we think of? Imagine a sheet of metal or whatever that you can chop without breaking, and you just chop it up into loads of little pieces in this way. You'll get these little rectangular boxes. We'll probably draw over here in a second. Now the one I'm interested in might be something in the middle, and I'll probably exaggerate the size of it. Chop, chop. So this is a bigger delta X than over here. They should be all equal. Chop, shot. And you can see here, I have a square in the middle. I know for later on it's important that this is delta x and this is delta y and that they're equal, but I think at the moment it actually doesn't matter. I'll just assume that it is just for the moment. So remember, this is actually a three-dimensional thing, so just give it its little bit of width. It's a little bit of a box. So if you take this bit out, and we'll just draw an arrow there. So take this. This is going to be delta v. Now we're doing this with fairly with finite delta x, delta y, and delta z. Delta z is supposed to be small already, but you can make delta x and delta y smaller ideally, and chop it up into a finer and finer mesh. So anyway, here's this delta v value. It seems to have gotten magnified as well. So this is zooming in on the delta v. The delta z is small. So you got a little piece here. This is this delta v. So this is delta x. This is delta y, and the width, as before, is delta z. So this is what's called a volume element. Okay, now for what we're talking about, I think it's important that this is small, but not infinitesimally small at the moment. Okay, I'll go slowly here because it's there's a few bits I don't want to mess up. So consider a volume element. We've done that. Now we've got associated corners. So we've got some, we have some, how we say, coordinates. So let's look at these corners. So I'm going to look at this corner here. And this has coordinates x, y. I don't have to include the z coordinate. And this corner here, this is x plus delta x, because you're moving along delta x, and y plus delta y. Okay. So, now, what is it about steady state? So if you think about, now, you're supposed to understand from, I don't know, what is it, thermofluids or something? You're supposed to understand your thermophysics. Basically, you've got heat and temperature. Heat essentially is energy, and the larger the heat, give or take, the larger the temperature. So you've got a little bit of volume here, and this can contain heat energy. And if you increase the amount of heat energy in this volume element, the temperature increases. And as all things come into it, I mean, if you, okay, we can talk about different things, but it's not too, okay, oh yeah, what I was going to say is, well, what is heat energy? Well, if you really go into the fundamentals, heat energy is particles moving around. Okay, but I don't really need to go into that. So, heat energy, and the more heat energy, the higher the temperature. Right. Now, if you have, say for example here, this edge is hot, and this edge is cold, what you're going to have is, we'll write this down a little bit later, when there is a difference in, now when I say hot and cold, I mean high temperature, low temperature. We're going to see there's something called Fourier's law, which says that heat energy flows from hot to cold. So what we're getting here is, if this is high temperature and this is low temperature, you've got a flow of heat across the plate. Now, if you start the plate perhaps at 0 degrees, and let's say this is 100 degrees and this is 0 degrees, what's going to happen? Well, if this is initially 0, you're going to get heat flowing from the hot temperature to the cold temperature, and as the heat flows in, and say it hits this little volume element here, as heat flows into this, the temperature of this is going to rise. And this is going to keep happening for a while, and that is called the transient state. Now, what's going to happen after a while is that, so you're going to have, the heat is going to be distributed around the plate, and the temperature is going to be distributed in such a way that this will still be, so this will be cold, this will be hot, and this will be medium, say. And what's going to happen is you're going to get a heat energy flowing from high temperature to medium temperature. So you're going to get heat flow into this volume element. But at the same time, because this is medium temperature and this is low temperature, you're going to have heat flow from the volume element out. So you're going to have heat in and heat out. And if you think about it, while there is more heat flowing in than go out, the heat energy is going to go up, the temperature is going to keep rising, but eventually you're going to reach a point where the heat energy in is equal to the heat energy out. And so say every second you've got whatever, say whatever, 10 joules coming in, 10 joules coming out. The total heat energy in here is not going to change. And if the heat energy in this volume element does not change, the temperature doesn't change. And so you eventually, after a while, this all settles down, it goes into a steady state where the temperature in each volume element becomes constant. So eventually the temperature settles down. And this is what your steady state is. And this is what we're going to study here. If we were to study how the temperature flow changes in time, that's the heat equation. We'll look at that a little later in lectures. Okay, so what we're going to do is we're going to say, okay, for steady state temperature, the heat energy in must equal the heat energy out. And if we can write down that equation, that is the equation of steady state. Heat energy into a volume element is equal to the heat energy out. Okay. So you have a clear idea. You should understand these concepts of steady state, and you should understand that concept of heat energy on a rough level. Okay, what do we got? The plate is insulated everywhere except at its edges where a boundary condition holds. So what we have to do as well is, well actually that's not too important. So the boundary condition is just saying that there is some temperature distribution across here. Usually it's constant. It could be different. It could be going from maybe 10 degrees up to 200 degrees. But as far as our differential equation is concerned, that is only a boundary condition. And you can talk about the partial differential equation without talking about the boundary condition, just like you can do with a differential equation. And here you see again a boundary value problem. What you know about the function is going to be its values on the boundary. Now you might say, what about the boundary, the top and the bottom of the plate? But they're actually insulated, so they're not really the boundary. Okay. So what have we got? The plate reaches a steady state when the temperature does not change in time. This is what steady state means. It doesn't mean that heat energy isn't flowing. There's still a flow of heat energy, but it's balanced. Let's say the heat energy in is equal to the heat energy out. The volume element, such as delta V, receives a net heat energy transfer. If more goes in than goes out, the temperature of that will rise. For the plate to be in steady state, the heat energy transfer into delta V must equal the heat energy transfer out. We've said all this. Note that the heat energy transfer is not uniform when in steady state. Okay, we'll describe what the hell that's about. Okay, imagine a pot of water boiling on a hob. I'm not a very good artist, sorry. That's a pot of water. Okay, well, it's supposed to be, God save me now trying to draw fire. Fire! Right, that's fire. And, okay, now we've got heat energy flow because now you could say this doesn't really get to steady state because the water evaporates and stuff. But let's say this isn't that hot. And what I mean by that is it doesn't burn, there's no water actually. Oh no, okay, look, it doesn't really matter. All I really want to say is that the heat energy transfer isn't the same. You've got more heat energy flowing here and less, say, over here. At each point you have a direction of the heat energy, which we'll talk about in a second. So say you've got a little bit here going along the handle. That's a small bit of heat energy transfer, and you've got big heat energy transfer from, well, let's say the flames into the thing. Okay, heat energy transfer from the hob to the bottom of the pot. Oh, I've got a gas cooker. This was supposed to be a hob. But anyway, through the base is very great, but the heat transfer at the end of the handle is not so great. Now, this system can theoretically reach steady state with various components at various temperatures, but nothing cooling up or cooling down. So this is maybe if we have a low temperature hob, water that isn't boiling, you can reach steady state. There's different heat transfers. There's still going to be more heat transfer at the bottom, but as it comes up quickly, it'll leave the bottom quickly. And you know, this can be at whatever, 40 degrees, the water might be 70 degrees, the very bottom might be 100. The important thing is that the temperature isn't changing. That's what steady state is. If you put the pot on the hob initially, well, the pot is probably initially at room temperature, 20 degrees. Putting it on the hob, the bottom is going to increase. That's more a transient state problem. Okay. Now, what we have here is we need to talk about something called the heat flux density. Now, what the hell is this? Now, first of all, I think on the next page we're going to turn it into okay. So, what the hell does this say? So, this vector, it does, I think, two things. It says, and there's a few things I might mess up here, but it's not too important. This is just a derivation. Why are we doing this, by the way? Well, you're not going to see partial differential equations again until fourth year, and this is your introduction to them. It's good that you see this before we go. Some bits of this can be examined. Well, you want to think it's all examined, but I mean, we're going to derive an equation. That's not examinable. Okay, so what the hell is this heat flux density? So we want to say, okay, look at this vector. This is supposed to be my heat flux density. The idea is kind of what's going on. It's got a direction. So for example, I could put an axis here. This is maybe the k direction, this is maybe the I direction. And it's also got a magnitude. Now, the question is, how do you measure the magnitude? And that's a little bit subtle. So let's write down that this thing is actually a vector. Now, the notation is a bit confusing. So this is at a point. So I should be able to try to draw something below. So you got a point, x, y, z, and you've got a heat flux density vector at that point. So it's going to go in some direction. So there's going to be, so this is the component of the x, the component of the y, component of the z. Arguably, this x, y, z and these x, y, z's are different. I might actually change here to x0, y0, z0. So this is a specific point. And we have this vector, it has some kind of a direction, and it also has a magnitude. Now, okay, there's different ways of explaining this, basically, and they might contradict something I do a little bit later on. This is okay, this is saying of this flux, how much is in the x direction, say that's like that. Okay, what do I need to get to? Right, the basic idea here with this thing is, okay, you've got heat flowing, and there's two elements that need to come into it. Essentially, okay, you got the heat flowing, and I mean, what's the difference between a big heat flow and a small heat flow? The basic difference is with a larger heat flow, you get more heat transferring in 1 second. So there's going to be a time element to this. So this is going to be, it's a certain amount of heat energy that flows in a single second. So this thing, if we're talking about units, let's talk about units. That's actually a great idea. Joules for heat energy per second. Now the next thing is, well, how? So what this is saying is, okay, in a second, how much heat energy flows. But then you've got an issue because, like, if you've got a really big fire, say, if you double the size of the hob, you've got twice the heat energy coming per second, but you don't want to say that it's actually twice as strong, it's just the same thing. So what you have to take into account is, in this case, the area, and in fact, this is going to be area in here, I'm fairly sure. So yeah, how much would flow through, now it might be meter cubed, it might be per meter squared, I'm not actually, I'll have to think for a second on that. I think it's meter squared, yeah, it's going to be meter squared. So what you do is, so you could have heat flowing for, kind of from loads of different points, but what you want to say is, okay, look at this heat, how much goes through maybe a unit area in 1 second. So imagine kind of putting a little